Hello friends, once again welcome to my channel, and in today's video we'll see one new topic, that is floating point numbers. Till now whatever operations we have seen or whatever operands we have taken, all were integers only, sometimes signed, sometimes unsigned. But when we do the real life problems, we come across many times floating point numbers. So how to represent them or how to store them in memory, how to perform their operations, to know all these things becomes highly important for us. So next, our treatment is for floating point numbers. So the floating point numbers are basically represented in your memory using IEEE notation. IEEE number representation is there for storing the floating point numbers. How to do it and all I'll be discussing in this video. So see, before going to this, how to represent it in all, why do we require floating point numbers, right? See, in your integer numbers, where is your decimal point? Whenever I'm writing one decimal number 123, the decimal point is fixed. Where it is? It is here, means after the number. There. But in case of floating point number, the decimal point used to float. It may be 1.23, it may be 12.3, like this, right? So it is floating. But in case of integer, that is fixed point number. Fixed point number means the decimal point is at a fixed position, that is to the right of the number, right? So see, when we are representing your this one, see, mostly our computer's word length is 32 bits. So to represent one number, we can use 32 bits. And using 32 bits, the number that we can represent, the maximum number that we can represent is 2 to the power 32 minus 1, if it is your unsigned number, right? So if the integer that is uh, represented using 32 bits will become this, right? We need not have to remember this number, just we should have an idea that what is the maximum magnitude it can have, right? So 2 to the power 32 minus 1 is the maximum number that I can represent using 32 bits. Why I'm talking about 32? Because mostly in my computers my word length is 32. What is word length is known to you, right? Then next one is, see, this is using 32 bits. That is, this is a maximum number. But when we do many scientific calculation, we come across many numbers which are bigger than this, right? That also I need to represent. But how many bits are there for me to represent a number? 32 bits. And the number that I want to represent is bigger than this. One example you can take, 6.023 into 10 to the power 23. What is this? Avogadro's number, right? This is 10 to the power 23, and here you can see how many places are there, right? But here 10 to the power 23. So it is a very big number that I need to represent. Then another, sometime when you are doing it, we have come across this number also, 9.1 into 10 to the power minus your 19. This one is what? This one is mass of an electron. This is a very small number, 10 to the power minus 19. So in the traditional method, the way we represent your this one, what is that? Floating point number means that 001, like this type of numbers. There we cannot represent this such smaller number, right? And we have mostly our word length to be 32 bit. And using that number of bits, I need to represent my operands, right? So see, for scientific calculation, we come across such bigger number, as well as that was not 10 to the power minus 19. Sorry, it was 10 to the power minus 31, because it is long back I did that. What is mass of an electron? So that mistake was there. Now see, electron mass is 10 to the power minus 31. So these small numbers are there. That small number and bigger number we need to represent. And in our hand, we have the length of our operand is 32 bit. So how to deal with the situation? We need to represent this number, and the operand length is what? 32 bit. Then how to deal with it, right? So but for representing such numbers, 32 bits are not sufficient in our conventional method of representing the numbers, right? In the binary, how we represent this will not be sufficient enough using 32 bits. Then to solve this problem, we have used one method. That the solution is nothing but IEEE 754 standard. Using this standard, we have represented the numbers using single precision and in double precision also. In single precision, we use 32 bits, and in double precision, that is two words number, that is 64 bits, we represent. There we can deal with all these numbers easily, right? Even in 32 bits only, we can represent these numbers. How we are going to do? That means how one number is represented using this standard, either in single precision and double precision, that we will see next. Before going to that, I will tell you some basic terms, introduce some basic terms. So suppose this is one number, right? In see, you must be knowing what is mantissa, exponent, scale factor, base of a number. This is my decimal number. So base is what? 10. What is mantissa? This part is called as mantissa. What is scale factor? This as a whole is a scale factor. And what is exponent? Whatever is there to the powers of 10. That is 23. So, see, this is one number, this is one floating point number. The number consists of three components. One is mantissa, one is base. Base is implicit. We need not have to store. One is exponent, another is scale factor. This also will not store. This also we are not going to store. So, mantissa, base, exponent, and scale factor. In our case, in this example, the mantissa is this one, right? So these terms we need to remember. Basically, what we are going to do in your IEEE format is that we, as a whole, whatever is the magnitude, that I am not going to store in IEEE. What I am going to store, this exponent I am going to store separately. This mantissa I am going to store separately. Then only this bigger number can be accommodated using 32 bits. That trick we are going to play. So see here, in IEEE floating point notation, the standard representation is used. There are two representations are there. One is single precision, one is double precision. Double precision means what? After decimal point, we can represent many more digits. And in single precision, lesser number of digits we can represent. So in single precision IEEE format, a number is represented using three components. One is sign, one is exponent, another is mantissa. Do understand, in IEEE also we represent our numbers in binary. So the base of our number system will be what? Binary, right? As a whole, the sign of the number is represented here, and the exponent may be positive or negative. That will be treated here in the exponent part, and mantissa will be stored in binary in this part. So here for mantissa we have kept 23 bits, for exponent it is 8 bits, and for sign bit only 1 bit, because 1 and 0 is sufficient to tell the number is positive or negative. Their greater treatment we will be doing in the next slide. Then in double precision, only values are changing. There also three fields are there: sign, exponent, and mantissa. Mantissa is 52, exponent is 11 bits, sign bit is 1, right? So actually using this single precision, in this 32 bits only, we can represent that 7-digit mantissa, and our exponent value can be 10 to the power plus minus 38. This much we can represent. So both Avogadro's number as well as my mass of an electron, both are accommodated using 32 bits only. That means that very big, that is 10 to the power plus 38, very small 10 to the power minus 38, both are accommodated using your single precision. So this is my that exponent part, and another, this is as a whole scale factor into 7-digit mantissa we can represent in your single precision. And in double precision, these values are going to increase. Here it is 10 to the power plus minus 108, and 11-digit exponent we can, 11-digit mantissa we can have. So next I am going to explain how this exponent, mantissa and all are going to be stored. See here, exponent is 8 bits. So using 8 bits, what is the number I can represent? The number that I can represent using your this one is your um, 0 to 255, right? Using 8 bits we can store the biased exponent. In IEEE, the exponent that we can store is 0 to 255, right? Using 8 bits. But my exponent can be both positive and negative. So if it is both positive and negative, then in sign representation the magnitude range will be what? Minus 2 to the power 7 to 2 to the power 7 minus 1, because it starts from 0, so it will go up to 2 to the power 7 minus 1. Why that 1 bit is left? Because 1 bit is for the sign of the exponent. So minus this one to plus this one. In this range, we can represent a exponent using 8 bits, right? But what we are going to do, we are not going to store the exponent directly in our IEEE format. Rather, we are going to store biased exponent. You may have come across one term, access code, EXCESS, access code in your digital logic. So here also that access code kind of thing we are going to do. That whatever is my access, that is nothing but bias. So here in bias exponent means in our IEEE exponent is stored in the bias format, and bias exponent says that we do not want our exponent to be a signed number. Rather, we want it only to be a positive number. We are not going to carry the sign bit, right? Only we'll take exponent as a positive number. But in my real life, my exponent can be both positive and negative. So what I will do with my negative exponent, I will add some quantity so that it becomes your positive value, and that I am going to store in my that bias exponent. Right? So to get only positive values, we are assigning bias. We are using bias exponent. So here what I will do, will add one bias, one number to the actual exponent, and that added result will be stored as the exponent of the number. Actual exponent I'm not directly storing. I'll be adding some excess bit to it, excess code to it, that I used to call as bias, so that it becomes positive. So what should be that bias, right? So see, maximum this one is minus 2 to the power 7. I need to make it positive. Say the exponent is minus 5, then it will be stored as what? Minus 5 plus bias. So what is my bias, right? What is my bias? So I need to make it positive or 0. So see, what should be my bias then? See, this is my least value, right? I need to make it positive. So what I will add? That 2 to the power 7. So using 8 bits, if it is using k bits, then it will be 2 to the power k minus 1. So if it is 8, 8 minus 1 is 7. If I'll add this to this one, it becomes 0. Then all other values will be positive, right? So bias is represented as 2 to the power k minus 1. And if the exponent is represented using k number of bits in general, right? So what we are going to do, we are going to use bias exponent. And why we are using bias exponent? We want to store our exponent only as a positive number, and there is also benefit associated with that. If we compare two floating point numbers, right, then if their sign is same, then the comparison becomes easier, operation will become faster. So we keep them in positive number as a positive exponents only. To keep it positive, the actual exponent may be negative also, so we'll add some value to it so that it becomes positive. So whatever is my least value, with that, the positive of that, if I'll add, then all other values will become what? Positive, right? So that we are going to do. So in the next video, again, I'm going to continue with my explanation of IEEE single precision numbers. Till then, thank you. If you are getting from my explanations, then please do not forget to like my videos and subscribe to my channel. Thank you.